Hello everyone, this is EC 637 and again Professor Bouman is traveling today, so I will cover the lecture today. And I think last Wednesday Professor Bouman covered introduction of digital halftoning. And by the way, did you submit the lab for halftoning already?
Yeah.
Yes. Oh, okay. So students knows the. I think most of this are halftoning. Okay, so this is going to be probably review, but okay. Last Wednesday, I think Professor Bouman covered constant digital halftoning, constant threshold, and ordered dither, and I think he stopped here. So today I will cover another digital halftoning method, which is called error diffusion. And then I describe how to implement it. And then also I describe the theory behind it. And actually, this doesn't exist in the note, but there is another method, which is called the search-based method. And this method uses optimization framework to find the best halftone image. And usually, like this method uses some iterative way to find the optimal solution. So it takes lots of time. But if you are interested in Professor Alabak and his student published paper, I think the halftone is, the name of the halftone is called direct binary search. So if you are interested in, maybe you can look up the paper. So, Okay, first I will review the digital halftoning very quickly. So digital halftoning, many image rendering technologies only have binary output. For example, printers can either fire dot or not. And for example, if we want to print this image, it's easy because this image contains only text and white background and black content. So it's easy. But if we want to print out picture which has continuous pixel values, then it's very difficult problem because we can express the picture by only binary values, which means black or white. So probably the simplest digital halftoning method is this, okay, constant threshold. And X is the input pixel value. And then we introduce a threshold. And if pixel value is larger than threshold, let's set 255, otherwise 0. And in halftoning, 255 is a darker color, so it's black. And 0 is white. So yeah, we can do halftoning just by thresholding. And actually this thresholding is same as a minimum squared error quantizer. Because we look up each pixel and then we want to decide which I will take, 255 or 0. And we take closer one. So this is same as minimum squared error quantizer. So in the equation, we are minimizing this cost. This is input, this is output. We are minimizing this squared error. So I think last Wednesday you saw this constant threshold method does not generate good results. Here are the results. Doesn't look great. First of all, like we lost all of the details, and plus, yeah, this lady does not look attractive anymore. Why does it happen? Because we optimize, right? Yeah, we optimize this cost. So in terms of this cost, it should be optimal. but the result is not good. Why? One of the questions is that the cost selection is bad. So maybe this cost is bad. Yeah, that's one of the answer. So actually, people already knew if we use different costs, we can get better results. And actually, maybe here. I think you saw this diagram before. This is the fidelity metric. Like when we compare two images and calculate quantitative error, we use this model. And here's a low-pass filter. Do you remember why we use low-pass filter in the fidelity metric?
Human visual system.
Right. Yeah, because our human visual system has a low-pass filter. So that's the reason why low-pass filter is here. And for example, like if we look image very closely, we can see the sharp edges. But if we look image from very far side, it's getting blurred. So it's kind of optical property of our human visual system. So, okay. This cost is bad because we didn't take into account of this low-pass filter property of our vision. So many people thought about beta cost function and also thought about the alternative method of constant threshold. So here's the example. Okay, let's say we have 4 pixels, and each pixel takes same value, 130. And this is mid-grade level uniform patch. And then let's apply constant thresholding method. And we picked t equal 127. Then what is the output? 130 is slightly larger than 127, so output is all 255. Okay. Then, our vision contains low-pass filter. So let's take average, because average is one of the low-pass filter. But this is uniform, so it's still 255, 255. Actually, this is very bad half-toning, because originally it's 130, but now it's mid-grade level became all black, so it's very bad, huge error. So what's the alternative? Let's pick this, for example. It's a little bit local variation into it. And then let's take average of this. What's the average? It's 150 by 1. So it's around 127, something like that. Actually, this is closer to the original, right? Almost same. This is very great. Yeah. So, okay, introducing some local variation works pretty good. And because our vision contains low-pass filter, so after taking average, if it's closer to original image, that's good enough. So these are introducing local variation. This method is called ordered dithering. And then I think last Wednesday, Professor Bouman introduced 2 methods. One is called cluster dot screening, and the other one is dispersed dot screening. And besides this, here is another method. Let's say we have 4 pixels, and we start from here and process the image like this. And then first, let's say, let's threshold this pixel. Using t equal 127. Then it goes to t55. But oops, okay, this value is very different from original value. It's increased a lot. So how about decreasing next pixel? Then maybe we can keep the average value same, right? This is kind of motivation of error diffusion. And I will describe details later. Okay, so first I want to review these 2 methods quickly. Is it fast, slow? Okay. 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 Ordered dithering. So I said introducing local variation was good thing, but how can we mix up 255 and 0 for different grade level? So here is one option. We can set different threshold for each pixel. So 0 means this is a low threshold. And 3 means it's high threshold. Okay, if we set a different threshold for each pixel, if we think about the uniform input, let's say 0, 0, 0, 0. And then increase the value little by little. And then if we apply this set of threshold to each different grade level, we can see the outcome. It grows like this. And actually, these are called dot profile. Dot profile. And clustered dot screening and dispersed dot screening, just how to grow this dot is different. For example, okay, clustered dot screens. So when we change the gray level, first, like we see dark dot here, and then it's grow like this, and always it forms one cluster. And so basically we change this dot in size as our gray level value increases. So if we use these clustered dot screens, actually outcome is like this. So we can see lots of clusters. And so transition between blocks is a little bit too obvious. Actually, if we look at this picture from very, very far side, it looks good. But if we look closer, we can see distinct clusters. And actually, in this cluster dot screening, I said we change dot size for different gray levels. This is also called amplitude modulation half-toning. Amplitude modulation. This is just like a different category of half-toning. Okay, and then another one is dispersed dot screening. Yes, okay. Dispersed dot screening is dispersed means basically spread out. So when dot grows, like first this dot, we start from this initial dot, and then next gray level we put the dot here, and next gray level we put a small dot here. So it's sparsed, but in terms of density, it grows. And this type of half-toning is called frequency modulation half-toning. Modulation half-toning. And then here is the results. And actually, compared to the clustered dot screening, the transition between blocks is much better than this. And those are the review of the last lecture. And then today I will introduce new half-toning method, which is called error diffusion. Okay. Okay. Error diffusion is a little bit different from the half-toning method we introduced. Before, we used the point-wise operation for the half-toning. Yeah, point-wise operation. So for each pixel, we pick up one pixel of interest, and then we do thresholding, and we get the result. So it's point-wise operations. But in this error diffusion method, we will use the information from neighborhoods. So in error diffusion, we process image in raster order. So raster order means here is the image, and we process from left to right, from top to bottom. So we process pixels in this order. And then we quantize in the result, but pushing the error forward. And people found out this error diffusion method is better than the half-toning, which uses screens, means dot profiles. So here is the actual example of error diffusion, but this is 1D case. So Fy is original image. Sorry, not image. Right now, we are thinking about 1D, so original signal. And then here, we use threshold 0.5. And then actually, final output, we want to get a binary value, 0 or 1. And then we start processing this data, and then we process like this. And first value, this is 0.25. So we apply thresholding. And because 0.25 is less than 0.5, so output is, it snaps to 0. Okay, now it creates error. What is the error? This is a definition of the error here. EI is F tilde I minus BI. So this 0.25 snaps to 0. So error created here was 0.25 minus 0. So 0.25. And then we want to propagate this error to next data. So next data original value is 0.25, but the previous data has an error, so we add this error to this. So it became 0.5. So okay, we adjusted this value. Then we apply binarization by thresholding. And 0.5 is equal or greater than 0.5. So now we snap this value to 1. So here again, this data generates the error. It's F tilde. This is 0.5. So F tilde is adjusted data is 0.5, and now it snapped to 1. So error was minus 0.5. So I want to propagate this error to next data here. So next data is 0.25. So add this negative number, so it becomes minus 0.25. And then we perform thresholding. So we just do this procedure repeatedly. And the final outcome is like this. Okay, now outcome is 0 or 1. And then let's calculate the average of this signal. Okay, here is 1.0. This is not binarized yet, but let's use this value. And then it's 6 data. So average is 0.25. Yeah. So look at the original signal. The average is 0.25. So average value was maintained even though we little bit manipulated each data. So this is a 1D case of the error diffusion. And how about the 2D case? Okay, 2D case. First, we initialize F tilde by original set of data. And then we binarize using the threshold T. And here's an example. Here's a part of the, we are looking at this pixel. And we assume that all of the previous pixels error are already calculated. And then we binarize this pixel. And then we calculate error. And then we want to propagate this error to neighbors. And in 1D case, we have only one neighbor. But in 2D case, we can have multiple neighbors. So in this case, we define neighbors is 1, 2, 3, 4 neighbors. And then also we can distribute error equally, or we can also put some weighting factor here. There's a common value to use. For example, there are many choices for weighting factor, but the popular one is here with 7/16, like 1/16, 5/16, 3/16. So this is a weighting factor, so sum is 1. And this weighting factor, this particular set of numbers is called Floyd and Steinberg error diffusion weights. Okay, so here is the procedure. Yeah.
Quick question. Do you know how they came up with those weights? I mean, it makes sense that they sum to 1.
Yeah.
But what was the rationale for having 7/16 propagated to the right and 1/16 down to the right?
Actually, it's a very good question. To be honest, I don't know how they came up with, but what they do care is first they care the computation. Computation shouldn't be too expensive. So, for example, like this here is like number is 16. 16 is 2 to 4, right? So in computer, it's easy to calculate.
Shifting.
Yeah, shifting. Yeah, we can implement by shifting. So they pick these numbers. Yeah, and yeah, also I think they consider this neighbor is closer to this, so more influence. So they pick little bit larger number than this one.
Okay.
Yeah.
Thank you.
Yes. And okay, this is the overview, and I want to show the actual example here, a very easy one. Okay, here I use this filter. This is a current pixel I'm looking at, and then if this pixel generate error, we want to spread only 2 neighbors, but equally 0.5, 0.5. And then I use again this threshold. And let's start from here. We assume this is the original image. Pixel values are all 80. And then first, so I said I process this image in raster order. So we start from this pixel and then process this way. So first we threshold this pixel. This is smaller than threshold, so we set 0. And then, okay, this pixel generate error. Error is defined by f tilde minus b. So 80 minus 0. So the error of this pixel is 80. And then I want to push the error to neighbors. How? We decided to use this equal weighting. So we for the error, this pixel and this pixel, which doesn't exist in this case. So we just consider this one now. So we add this value to this one. So f tilde become 120 now. And then, okay, now we do thresholding for this. Still, it's less than 127. So we put 0 here. And then again, we need to calculate error. And then, so now error is 120 minus 0. So here it's 120. And again, we want to propagate this error to two neighbors, this one and this one, half and half. Yeah. So if you look at this f tilde, this is 80. So this becomes 140. This 180 plus 60, so 140. And then repeats the procedure. Okay, now we understood how to implement it. But actually, there are two different point of views for the error diffusion. So, okay. I said I binarize this pixel, and then I said I want to spread the error to neighbors. So this is a point of view of the person who provides error. But what if, let's say, in this case, this person, this pixel receives the error from this person. Let's think about this way. Okay, we are looking at this pixel. Which neighbors gives error to this person? Does it make sense? Yeah. So we are looking at this pixel. This pixel gives error to this person? Yes. Yeah, obviously, yes. How about this pixel?
Yes.
Yes. So basically, we can, move this relationship spatially. Okay, how about this person? This pixel gives error to this person? Yes, yeah. How about this person? Yes, yeah. So, from point of view of this receiver, these are the pixels which gives error to him. Okay, this point of view is called the pooling errors forward view. Okay, this is exactly, we are talking about exactly same thing but just different view. And as I told you, this pixels receives error from these neighbors. And actually, this point of view is very useful because we can draw a system diagram from this relationship and we can analyze. So what does it mean? Okay, if we draw a system equation from this relationship, actually we can write the equation like this. So f tilde adjusted value equal to original value plus collected errors from neighbors. And I want to mention, actually, so this is a forward model. We have number here, and actually we can fill corresponding number here. So here is a corresponding number, and again the sum equals to 1. And then, okay, so these numbers corresponds to this value. And I have a question to you. Okay, Professor Bouman's favorite question. Okay, sum of h equals to 1. Is this low pass filter or high pass filter? Yeah, low pass filter. Yeah. So this is low pass filter. Because this is a DC component. So when we draw a spectrum, DC component is 1 minus 1. So at least this is a low pass filter. Okay, so here's the system equation. And then using this F tilde, we can binarize to get the final output. And then now we can calculate the new error, E equal F tilde minus B. And then this new error is propagated to next neighbors. Time passes very fast. Okay, here is the summary. Sorry, I little bit switched the order of the handouts, but so there are two views of error diffusion, two mathematically equivalent views of error diffusion: pulling error forward, pushing errors ahead. And then we first look at this one, pushing error ahead. This is more intuitive. And pulling errors forward, this is not intuitive, but it's more analytical, or maybe signal processing point of view. And okay, from now on, we use this view to analyze error diffusion more. Okay. We already know this system equation. This came from this point of view. And then based on this system equation, we can actually draw a system diagram. So this system, this equation corresponds to this summation. So F tilde is original image plus corrected errors. And then we binarize this F tilde here. We quantize. And then we calculate new error here. This corresponds to here. This equation corresponds to here. Okay, so using this system diagram, oh, by the way, I want to mention, actually, please notice that there are two different errors in this diagram. One is E. This is called a quantization error. Another error is let's see, maybe here. Bij minus Fij. This this is the final output. This is original. And in this node, this error is called display error somehow. But this is overall error. Overall error. And obviously, we want to minimize this error. But actually, it's okay to contain high-frequency components in this error. Again, why? Yeah, because our human visual system has low-pass filter. So this error, it's okay to contain high-frequency component, but not low-frequency component. This is okay. Component. So in other words, when we analyze this error, if it contains only high-frequency component, this is a good half-toning method. Okay. Actually, I'm a little bit messed up the order, but just in case. Just this is some choices for the low-pass filter H. So I explained all of them using this coefficient, but there are any other choices. Instead of using 4 neighbors, we can use much more neighbors. Just a computation gonna be expensive, but this generates some artifact, but this has less artifacts, but computationally expensive. So here is the example of the results by Floyd and Steinberg on diffusion error weights. So actually, compared to the digital halftoning using screens, actually this outcome is much better. So, okay, here's a halftoning using cluster dot screening. Compared to this, error diffusion looks much better. It contains more like high-frequency noises, but outcome turned out to be very good. Okay, now we still want to continue to analyze error diffusion. So first, I want to little bit introduce commonly used model for the quantization error. So here is the system diagram, and then this quantization error, it's often assumed to be white noise. And actually, if we assume these 3 components, we can derive this. And then we can say this quantization error is a white noise. And maybe let's derive this a little bit. Okay. For example, okay, EIJ. Just notation. I use XIJ instead of EIJ. Okay. Here's a proof. EXIJ. This is we assume this is a uniform distribution. So this is a -0.05, and then 1. This is x dx. So if we calculate this, the mean equals to 0. Okay, how about this one? first we think about the k equals 0 and L equals 0. There. Again, this one can be calculated in a similar way. So, just and if you calculate, it became 1/12. Okay. How about the other case? Otherwise, xij xi plus k j plus l. Because of this assumption, this is uncorrelated, so we can separate it. Xij. Sorry, I don't have space, but this fills here. And actually, we already know mean equals 0, so this equals 0. So overall expression of this become delta function. So here is a proof. And then this error is called white noise. The reason why it's called white noise is okay. Oh. Be here. Okay. Let's try to calculate power spectral density. Power spectral density is a tool to analyze a random signal. And then, fortunately, we can calculate power spectral density easily for the wide sense stationary signal case. And actually, this is let's say this is a power spectral density. Then there's a theorem we can calculate power spectral density by using Fourier transform of autocorrelation. And actually, this autocorrelation is this one. This is autocorrelation. So if we take Fourier transform of delta function, what's the Fourier transform of delta function? Yeah, it's 1. So it becomes constant, right? So basically, I draw 1D case, but this means it takes constant value over different frequency. So actually, shape is very similar to the white color. For example, white color, like it's visible light. White color can express like this, like visible light is between 400 nanometer to 700 nanometer. And then this is more blue color, right? And this is red color. And then white color contains all of the frequency components. So shape is very similar. So that's the reason why it's called white noise. And then, okay. Maybe I don't finish the analysis, but the direction we want to go is basically this is the current system diagram we got, and then actually we can prove this system diagram exactly same as this one, same each other. And then actually we can see error diffusion. Using error diffusion, the overall error contains only high frequency components by using diagram. But I will leave it to Professor Bouman.